Hi everyone, welcome to this video. My name's Jaimie Platt and I'm a final year PhD student at the University of Liverpool. Hopefully in this video I'll be able to talk about some of the research that I've undertaken at the University of Liverpool Physics Department, specifically developing new ways to characterise radioactive waste. Hopefully this video will give you an insight as to how some of the topics that you've been learning at A-level can be applied to university research. I'll just give a brief introduction to myself before we get started, but then I'll talk into the research that I was able to undertake at my undergraduate level degree and also the current research that I'm undertaking as a PhD student. So a brief introduction about me. Firstly, I did my A-levels in chemistry, maths and physics, actually obtaining my A grade in chemistry. It wasn't until I was applying for university that I knew that I wanted to do physics, specifically physics with medical applications. I was very interested in the career path that medical physics could offer me. I graduated from that in 2015 and then proceeded to do a master's degree in a subject called radiometrics, instrumentation and modelling. It gave an in-depth view as to the different radiation detectors and spectroscopy of different radiation types. And then finally, in 2016, I started my PhD in nuclear physics. And I'm still continuing that right now. So with the undergraduate research, as part of my bachelor's degree, everyone does a final year project based on the subject they're doing. Because I was doing medical physics, mine could be related to either the medical industry or nuclear industry. And the interesting thing about this project was that they had real life applications and potentially a real life impact as well. And I'll just talk to you now about the project that I was able to do. So my final year project was from the management of radioactive waste from medical isotopes from a local hospital. Now, this project was in collaboration with a local hospital to measure their radioactive waste. If you know or anyone has had any type of imaging that's done, if radioisotope is administered to the patient, the needles or the bedding that the patient's been in, they become radioactive and they have to be disposed of correctly. They can't just be thrown in the bin or disposed down the drain. There's lots of regulations that have to be adhered to. So waste is stored in these bright yellow bins that you can see in the image here, and they are usually put in a waste storeroom. Because they are sometimes at a high level for dose, they are left in the storeroom to decay away naturally until the dose is at an acceptable level to allow the waste to be disposed of. But the current method of detection to check if these waste bins are at a suitable level is with a Geiger counter. Now, for those of you who may or may not be aware of how a Geiger counter works, it gives no spectroscopic information about the radiation that it is measuring. It gives clicks that tells you how active or inactive a source is. So whilst that may be useful for a very quick test to see if one of these waste bins is very active, it doesn't tell me what radiation is in the bin, and it doesn't tell me other things that are quantifiable information such as the dose that is coming from the surface of this bin. So the hospital wanted a cheaper, particularly a more efficient way to dispose of this waste, and also a method to be able to clearly identify these radioisotopes that would be present in each bin. So before I go into some of the results that I'll talk about, I'll introduce you to nuclear forensics. Now, all radioisotopes that undergo gamma decay will have their own gamma fingerprint. And what I mean by this is that the energy spectrum that's produced will have very particular features that are specific to each radioisotope. So that means when the gamma decays and it deposits its energy in a detector, that energy is very specific to the radioisotope that it's come from. And it will differ for every single radioisotope, which means if I collect an energy spectrum, I should be able to identify what source I was measuring just from analysis of this. So from this, I would measure the gamma rays emitted from these bins with this setup that you can see in this image. On the left is one of the smaller waste bins that the hospital had, and to the right you can see here is our gamma ray detector that we used, and it was great because it was portable and it allowed us to take it to the hospital and it allowed us to bring it back to the university for my analysis. I would then analyse the spectra that is produced from these waste bins, and I would estimate the radiation levels at the surface of each bin, producing a surface dose rate to relay back to the hospital so that they can manage their radioactive waste a bit more efficiently. Now, the project had some interesting results, and I just want to show you one of them. One of these waste bins that I was given was labelled with technetium 99M. Now, this is a radioisotope that's used in diagnostic imaging in hospitals, and it corresponds to a peak, so a gamma energy peak at 140 keV, and it has a half-life of 6 hours, which means it's suitable for imaging because the radioisotope will decay away quite quickly. Now, the energy spectrum should look like this. The highlighted area in green shows the 140 keV peak that corresponds to technetium 99M. However, after analysing this bin, the energy spectrum showed more photopeaks, as shown to the right. As you can see, just from visually looking at between the two, that they're not the same. And by analysing the different peaks that are in this spectrum, as we can see with 24, 172 and 245 keV, these actually correspond to indium-111, another radioisotope that is also used in diagnostic imaging at hospitals. Now, the key difference with this radioisotope is that it has a half-life of 67 hours. The problem arises here when initially the waste bin would have been stored in the room for a time that would have amounted for technetium to decay away completely. However, probably with analysis with the Geiger counter, after potentially 18 hours or a day, you would have realised that it's still significantly active, but they wouldn't know what is in that bin without analysis with this new method. So it turned out the waste bin had been incorrectly labelled by hospital staff. Through my work and my results, this could be relayed to the hospital to hopefully improve how they manage their radioactive waste. So this was just one of the ways that my understanding of radiation and analysis of spectra could be applied to an actual real life setting. And the rewarding thing for me was that my local hospital was able to utilise my results and hopefully use them to improve their radioactive waste characterisation. Now I'm going to just talk to you about my current PhD research. My research is focused on this gamma imaging system that you can see in the image here. It's this portable system that utilises 3 gamma ray detectors to identify the location of radioactive sources. Using our knowledge of how radiation or gamma rays interact with matter, we can identify where the source of radiation is coming from. And this particular detector system has applications in both medicine and nuclear through the imaging of potentially medical radioisotopes, or for my particular interest is imaging radioactive contamination at nuclear sites. We are able to use specially made reconstruction algorithms to produce images, as you can see here, and these images would have been taken from the analysis of medical-based radioisotopes, and you can see how we were able to identify that there's 3 different sources present through these particular images. And what we want as a whole is we want to be able to extract important information from these images, such as activity and dose, not just the specific location that each source is at. For my particular work, some of the images that you see here is just part of my PhD research. Because I want to investigate its feasibility in a nuclear setting, I wanted to investigate how well it works with scattering material present, i.e. concrete walls. So the first thing that I look at is, can I identify radiation within a concrete wall and locate it to a specific brick, for example. This is important in a nuclear setting when you don't know where the radioactive waste is located, and pipes or part of the wall, drums, they may have to be disposed of correctly. So being able to accurately identify where the source is located can be hugely beneficial for the nuclear industry. Another thing that I was looking into was how could it be determined how much concrete that gamma rays have passed through? Is there a relationship between that with our very specific detector with the amount of concrete, the thickness of it, and the intensity of radiation, and being able to find a relationship between the two, which again can help in the nuclear industry in being able to help with this disposal of radioactive waste. Our overall aim for this system is to have a fully portable system where we can characterise radioactive waste in an industrial setting, and ideally to be able to take these measurements in complex scenarios. Things aren't always as perfect as being able to take measurements in a lab, so it's beneficial if this system that we have can take measurements in areas with high levels of background radiation, but where it can ignore that and it can focus specifically on the contamination of the radioactive waste of interest and be able to localise it and then therefore dispose of it in the correct way. Thank you all for watching. I appreciate your time in this video. If anyone has any questions about the research that I've undertaken, my contact details are on the University of Liverpool Physics Department website. Thank you again for watching, and I hope you enjoy the rest of this outreach.